So I hope you can hear me. So I'll be talking about the Lilliput effect. Is there a Lilliput effect, basically? Yes. So you're potentially all familiar with some of these evolutionary rules or some of these patterns that there's, on one hand, this tendency of evolutionary lineages to increase in size over time. And there's often coined this other effect, which is called the Lilliput effect, that we get somehow a decrease in size across evolutionary crises or extinction events. And that's, well, the thing I'm interested in this talk. So how can we resolve this? Well, first we need a lot of data. So for this purpose, we collected a lot of data myself, mostly for me with balanites, and a lot of other people in our project, which I will explain in the end. And then a lot of data from the literature went into this. We focused on marine invertebrates because, well, it's part of our project, and well, we have to start somewhere. We ended up with, well, about 250,000 individual measurements and about over 6,000 comparisons of samples. So we go from one sample to the next. It can be a species, it can be a genus, and then we see what's going on there. We also used some other kind of data from Gene Hunt. People might be familiar with these data where he was looking at trait changes over time, and we extracted the size data and another data set. I don't want you to read all of this, it's just if somebody would be particularly interested in this. So what do we want to do? So 4 things we can do with this data, or at least part of it. First of all, is there a Lilliput effect? Because it's a quite anecdotal thing. Some people observe a decrease, they report a decrease, they might just not report an increase. So we need to figure out if that's robust. Also, do different taxa respond differently? It's another thing we can ask ourselves. Another question is scale dependency in time or stratigraphic resolution or temporal resolution. So basically, if we're looking at two samples between different stages or from bed to bed, it might be quite different in the pattern that we see. And then we can ask what is actually controlling the Lilliput effect. So we'll be discussing the Lilliput effect in a quite broad context because I'm just looking at samples of assemblages. It can be an assemblage of a species between the two samples. It can also be higher lineages, which we are looking at. And then the last thing, well, we go into is just, does it really correlate with extinction, or what is actually this effect? If it's there, what is actually driving it? So we can wonder then, what's going on? Is it really good to be big, and or is small better during certain phases? That's a question we can ask. So we compiled a lot of data, as we already said. So if we go in the literature, or each person or each paleontologist measuring fossils, they do this quite differently. Sometimes you can have a PCA loading, you can have volumes, you can logarithmic values, and all kind of strange parameters. Luckily for me, many of them still use the millimeter, so we all brought all the measurements down by doing some transformations so we can actually compare those measurements. So how did we do this? I think it's very important because if, for example, we are looking at foraminifers and, well, foraminifer, maybe a large foraminifer is going 1 millimeter down, it might be quite significant, but if a whale goes down for 1 millimeter, we might not even pick that up. So we need to have a logarithmic scale for that, or proportional change. So what did we do actually? So this basically shows the change from a large squid to a small squid, and then the result would be a negative value. And the opposite can be done for ammonoids, for example, in this case, where you go from a situation where you start small and then you become big. So basically, kind of saying from one sample to the next, you have the Lilliput effect, or you have the Cope's rule, or some of these effects. So this is the result. So at first you think, wow, all this data here, and basically I don't see anything. What's going on here? So basically you have decreases, increases, but there seems to be a quite symmetrical pattern. I've always put this David and this Goliath thing, I had this in for GSA, so I thought I'd just keep it here. So basically if David is here, it's a decrease, and if the value is positive, it's an increase. So then we can say, well, okay, that's all very nice, but what do you do if you pool the samples and you pool them into 3 kind of groups? One is if you go from one sample to the next into a crisis, or if you go outside of a crisis, which is here called recovery. It's maybe a quite different definition. or you're in a background phase. And maybe you see something more. So it's also statistically robust, is that you have, during a crisis, on average, more chances to have a decrease, and in the immediate aftermath to have an increase in size. Then you can look at different groups. I don't want to have the details, it was just to illustrate like this multiple regression model where we looked at different groups, and you see that many of these taxa show the same pattern. So you can go from planktonic forams, conodonts, ammonoids, and some show slight differences in these patterns. And then maybe the most interesting thing is, because everybody associates maybe the Lilliput effect with a decrease in species and also in samples. But what's going on here? So if we look at first in taxonomic resolution, yeah, so we can look at measurements from today over years, and you see that this is actually the same kind of value, but it's the absolute value. So it's both increases and decreases, just the absolute value. And what you see is actually that if you are looking at comparing samples in very coarse temporal resolution, that, well, you have a tendency to increase or decrease a bit more than when you're just looking at years, which maybe makes sense, right? And the similar thing is actually happening on taxonomic resolution. So there is not much difference between the things we looked at, species and genera, fossil record, the data that we have. But if you go to families, orders, or classes, there is more variation in these patterns, and also the tendency to have large changes increases a little bit. So maybe the most interesting part is then, this is all very nice. You pool together in extinctions, but are all the extinctions the same? Are all the changes always the same? Is there really like a general mechanism which is going on? So we make like a time series. So it's again this log metric thing. So decreases, increases. And this is from the middle Miocene to the Holocene with the data that we have. And there you see that actually there's not a lot of changes going on. Also the KPG is, well, here is the KPG and there is the PATM, but well, it's slightly decreasing, but it's not like spectacular. I mean, some background changes could never be larger. And then the Tuacian comes up. Maybe it's because I work mainly on the Tuacian, so maybe this is a coincidence. I hope not. It doesn't seem to be. But the major decreases here. And also the end Permian extinction, it seems to be very similar. And we can do a kind of repeat where we just look at which of these kind of extinctions, so end Devonian, also the Endovisian. There is nothing happening in the Endovisian, at least in the data that we have. So the early Jurassic shows the most severe decrease and increase in size, and then there is well, over the extinction, so to say, or the second order extinction. Also the PTM slightly shows up, but I don't know what's going on with the recovery. So there are some differences between these events. A last thing is that this is all very nice. This is also a very heterogeneous kind of data set. What if we would look at, for example, belemnites? Yeah, so it's maybe a complicated graph. I will try to walk you through it. So basically, these are just some zones. So this is the boundary between the Punsbachian and Tuacian, and this is the Toai. So I took the liberty of representing this by two volcanoes. So there is like a hyperthermal event or a warming event here, and the same seems to be happening here, where it's also showed with this anoxia. And what I want you to see is we measured samples of belemnites. So we took robust samples of belemnite sizes, and then you can actually see we have decreases when the arrow is going down or increases when it's going up. But we can decompose this in three components. First of all, one is if you have a within taxa effect, which means that taxa reduced in size are just the same species reduced in size, which are already there, or increase in size, or these other two colors here, which are appearance or disappearance effect. So taxa going extinct or appearing after the extinction. And what you actually see is that during this first crisis, there is a very big component of size within taxa, which are decreasing in size. And during the second taxonomic turnover between the belemnites, there is not much within. So the Lilliput effect doesn't seem to be much there. It's actually increase in size, and it's basically driven by taxonomic changes. So this is very important, maybe I haven't hammered this enough, because we want to know what's happening with body size today. Everybody always models from the situation where you go from a background situation within lineage size change, but extinction can have a very different effect on the things that we see. So it affects our result. This is also what maybe can partially explain how we can put these models together. So some people might be familiar with the work of Jonathan Payne. He had a very big article in Science, I think, where he actually showed that today there is so how selection against or warming large forms would be more prone to go extinct. So selectivity against size, but it seems to be different when you go back in the past. But this is also the same if you would look at this data set that we had. The same is for origination, so there is more origination of smaller forms. And so then you can wonder, how do we bring all these things together? Well, I think it's not that difficult. So basically, the first good thing is maybe we can be confident that the Lilliput effect seems to be a thing. Yeah, so whatever you want to call it. Also, there seems to be some changes across the taxonomic level in stratigraphic grain, but it's not, we can potentially even correct for that. And then the most important part maybe, what is explaining it? So we cannot explain it really by extinction or origination really, or it doesn't seem to be the major thing. The Lilliput effect, as it is originally also defined, seems to be within limits, size changes to stress, and also abundance changes. And sometimes it's happening also before. And then I had one last kind of request. People working with a lot of data, I measure a lot myself, but I want to compare it with other data sets, and then it becomes a bit tricky sometimes, because there is not so much data. Not everybody provides their data. And if we want to do this kind of analysis and also compare our data with others, we need to more provide our data measurements and make them available to us. So yeah, so that was it, what I wanted to say. Thank you.